Today we've got the 14th video in our series on abstract algebra. And we're going to look at homomorphisms as well as some very important theorems, well, one certain very important theorem involving homomorphisms. If you recall, we looked at the definition and some basic examples of homomorphisms several videos ago. But since then, we've mostly been dealing with isomorphisms, which are homomorphisms that are bijective. And we didn't really dive into some structural theorems related to homomorphisms. And that's what we want to do today. Okay, so let's recall the definition of a homomorphism and then define a couple of parts of groups associated to homomorphisms before we get started. So let's say we've got groups G1 and G2 and a function which we'll call phi that goes from G1 to G2. Then we call that function a group homomorphism, or if it's kind of obvious that we're dealing with groups, we might just call it a homomorphism. Okay, so we call it a group homomorphism if for all A and B in G1, we have phi of AB is equal to phi of A, phi of B. So where this is understood inside here to be the operation inside of G1, but this is understood to be the operation inside of G2. So you've got this factoring action for this map phi. Now there are some important subsets associated to a homomorphism. The first one is called the image. So the image of phi, well, that's just equal to the image of the whole set G1 under the map phi. That's really just the range of phi if you think of it like a function. So it's all y in G2 such that y equals phi of x for some x in G1. And then next we've got this notion of the kernel of phi. And this is like essentially a more general version of the null space that you learned in linear algebra. So the kernel quickly is everything that gets mapped to the identity inside of G2. So we would write kernel of phi equals all A in G1, where phi of A equals the identity, where this identity is understood to be happening inside of G2. Then I'd like to point out that this is exactly the pre-image of the singleton set E. Or in other words, the singleton set containing the identity, which is most definitely not just a subgroup of G2, but it's a normal subgroup. It's the trivial normal subgroup of G2. Okay, so let's look at this first proposition. So we start with a homomorphism from G1 to G2, and then we have a subgroup H of G1, we have a subgroup K of G2, and a normal subgroup N of G2. Then we'll prove three statements out of this. First, the image of H is a subgroup of G2. Okay, so let's maybe just jump right into that one first before we even state the others. So we will prove all of these using the subgroup test. And then maybe since we're going to use that a lot here, let's recall what the subgroup test is. So maybe I need to use a little different letters here because I've taken up G1 and G2 and all of these kind of things. Maybe I'll use A is a subgroup of B if and only if for all X and Y in A, we have X, Y inverse is also inside of A. And let's recall that this like less than or equal to symbol, when it's put into this context of groups, means subgroup. So like I said, this is called the subgroup test, and that's what we'll be using throughout for number 1 and number 2. Obviously for number 3, we need to use the definition of a normal subgroup, which we'll get to. Okay, so let's do number 1. So let's suppose that X and Y are inside of this image phi of H. But now let's unpack that using the definition of the image. So that means that we have an A and a B inside of H such that X equals phi of A and Y equals phi of B. Okay, nice. And now let's just straight up calculate this xy inverse object using this version of x and y. So xy inverse will be the same thing as phi of a times phi of b inverse. But then by properties of group homomorphisms, which we proved before, we can push this together to get phi of a b inverse. But let's notice that AB inverse is inside of H. That's because we're assuming H is a subgroup of, let's see, G1. So that means this is inside of phi of H. But that's exactly what we needed to do to show that phi of H was indeed a subgroup of G2. We started with xy in phi of H, and we ended with xy inverse is in phi of H. Okay, good. So now let's look at this second statement. So let's notice the second statement has something to do with pre-images and subgroups. It says that if we've got a subgroup K of G2, then the pre-image of K under the map phi is a subgroup of G1. Again, we're going to use this subgroup test again. So let's suppose in this case that A and B are in phi inverse of K. Okay, and then what we want to show is that AB inverse is inside of phi inverse of K also. Okay, but then by the definition of the pre-image, we can turn this into phi of A, phi of B is inside of K. That's exactly the definition of the pre-image of a set. But now let's notice that since K is a subgroup of G2, we know that phi A, phi B quantity inverse is an element of K. That's by the subgroup test. But now we can push these two things together using the fact that phi is a homomorphism. This gives us phi AB inverse is an element of K. Again, by pushing those two together. But if phi AB inverse is an element of K, then that means that AB inverse is in fact an element of phi inverse of K as needed. So now we need to move on to number 3. So let's see what number 3 is. That has to do with pre-images of normal subgroups. So let's maybe recall what a normal subgroup is real quick just to get us started. So let's recall that, what is it? Well, we need some different different letters here again. Maybe we'll use this A and B over. We can't use N's and G's because we have those up there and it would be a little bit confusing. So let's recall that A is a normal subgroup of B if and only if A is a subgroup of B and it satisfies the following condition. So for all A in A and B in B, we have B inverse is an element of A. So that's the definition of normality, or one of the equivalent definitions of normality for subgroups. So now let's look at our third condition. Okay, we need phi inverse N to be a normal subgroup of G1. Notice it's already a subgroup of G1 by part 2, so we only need to check normality. So let's take, maybe I'll call it N inside of phi inverse of N, and then we'll take a little g inside of G1. And then by this definition right here, we need to be able to do this conjugation action and end inside of, in this case, phi inverse N. So let's see how that might go. Okay, well, let's notice that by this setup, we know that phi of N is inside of N. That's the definition of the pre-image. And sort of like in parallel, we know that phi of G is in G2. Oh, but N is normal in G2, so now we will use that. So let's use that fact to say that phi of G, and then phi of N, and then phi of G quantity inverse is inside of N. Again, that's by the normality of N in G2. But from that, it follows, using the fact that this is a homomorphism to push these together, that phi of G in G inverse is inside of N. That's just rewriting this left-hand side. But that condition right there is exactly what we need for G in G inverse to be inside of phi inverse of N, which is exactly the condition that we need for phi inverse of N, or the pre-image of N, to be a normal subgroup. So that proves all three of these statements. Now let's look at a corollary of that result. And this is a super quick corollary. It says the image of a homomorphism is a subgroup of G2. And that follows because G1 is a subgroup of itself, and the image of any subgroup is a subgroup. So that's really all there is to that. And then the next one says that the kernel of phi is a normal subgroup of G1. And that's because the kernel of phi is the pre-image of the trivial normal subgroup. But since this trivial group here is a normal subgroup, its pre-image is normal. But that makes the kernel a normal subgroup of the domain. And this actually raises the really important and logical question, which is anytime you have a normal subgroup, you want to think about the quotient group. And what is the quotient group of G1 with the kernel of phi? Well, in fact, that'll be the topic of the most important theorem of the day. But before we get to that, I'd like to look at this lemma. And this lemma is often thought of as like a better way to prove that a homomorphism is injective. In fact, it can be seen as like a different definition of injectivity almost. Okay, so let's see what we have. Given a homomorphism phi from G1 to G2, phi is injective if and only if the kernel of phi is equal to just the set containing the identity. So in other words, the kernel of phi is trivial. Okay, so this is an if and only if statement, so that means we've got two things to prove, a forward direction as well as a reverse direction. So let's do this forward direction first. So let's suppose that phi is injective and that maybe something that we'll call G is inside of the kernel of phi. But notice that G being inside of the kernel of phi is exactly the same thing as saying that phi of G equals the identity. Oh, but if you recall from properties of homomorphisms that we proved a few videos ago, the identity is always sent to the identity. Where, of course, we have to worry about context here. This is the identity inside of G2, whereas this is the identity inside of G1. So if you want to subscript these with 2 and 1, you can, but I don't think we really need to worry about that. That being said, this would be subscripted with 1 if we needed to do that. Okay, but now let's notice that by injectivity, since phi of G equals phi of E, we immediately get that G is equal to E. Oh, but that means that G is an element of the set containing the identity. So that means the kernel of phi is a subset of the set containing simply the identity. And that's just by set inclusion. Oh, but then notice that the other direction is pretty clear, that the identity is definitely a subset of the kernel of phi. In fact, we just use that for this equality right here. So that together with the other sort of obvious one tells us that yes, the kernel of phi here is trivial. In other words, it contains only the identity element. And now we'll move on to the reverse direction. While we're moving on to this reverse direction, I'd like to point out one more time that if you're given a homomorphism and you're asked to prove that it's injective, 9 times out of 10, you'll want to use this statement over here to prove it's injective. You'll want to show that the kernel is trivial. That's generally a faster way to do it than doing it by the definition of injectivity. Okay, so now back to this reverse direction. So let's suppose that the kernel of phi is equal to simply the identity element. So the kernel of phi is trivial, and that we have something that I'll call A and B inside of G1 with phi of A equals phi of B. So that's our setup for an injectivity proof. Okay, but if phi of A equals phi of B, that means that phi of A, phi of B all inverse is equal to the identity, just by right multiplying by phi of B inverse. But then from here we can smush those two things together using properties of homomorphisms to get phi of AB inverse equals the identity, but phi of AB inverse being equal to the identity is exactly the condition for AB inverse to be inside the kernel of phi, which we have assumed is equal to just the identity. Okay, but if we've got an element inside of a singleton set, then it has to be equal to whatever that thing is inside of that singleton set. So that means we have A, B inverse is in fact equal to the identity, but then again, right multiplying by B in this case will give us A equals B. But then starting here and ending here is exactly the injectivity condition. So we've proven this lemma. Now we're ready for a quick motivating example before we look at something called the first isomorphism theorem for groups. Now for that general example, let's take G to be any group at all and N to be a normal subgroup of G. Then we'll take pi to go from G to the quotient group G mod N. And we'll define that by G is sent to the coset Gn. And now let's just recall this notation right here. This notation with the arrow with the little like foot there is the same thing as saying that pi of G is equal to Gn. But this is like, a pretty common way in algebra to write these things down. Now, I'm going to first check this as a homomorphism, determine its image and its kernel. Then we're going to put these things together to guess at maybe a general result. So let's first check that this is a homomorphism. So let's take two arbitrary elements x and y in G, and we want to look at pi of xy. But let's notice that by definition, that is the coset xyn. But since n is a normal subgroup, we know that this is a group over here, and then this is equal to the coset of xn times the coset of yn. Remember, everything is well defined here because again, n is normal and we're in a quotient group. Okay, but then this is exactly equal to pi of x times pi of y. But that's exactly where we needed to end up for this to be a homomorphism. So now let's make the following claim about the image. The image of pi is in fact everything. It's G mod n. And that's essentially just by our construction of this thing right here. This is sometimes called a projection map, but the word projection means we probably should hit everything. Okay, so let's see how to do this. Let's take an arbitrary member of G mod n, but that arbitrary member will be a coset. So we'll call it Gn. And then we'll notice that we can most definitely find a pre-image of this, and that is pi of G is sent to Gn. And that's because this little g is inside of G, just by the definition of G mod n. That's how we construct those things. Okay, now let's look at the kernel. So let's suppose that we've got a G inside of the kernel of phi, and let's see what that means about our G. Can we get some more structure into this G? Notice that is equivalent to saying that phi of G is equal to the identity in G mod n. But let's recall that'll just be the identity coset. So that's where we have to use the fact that we're inside of the quotient group here. The context of our group matters. Okay, but then using the definition of pi, sorry, this should have been a pi, that's the name of our homomorphism in this case. So using the definition of pi, we have the coset Gn is equal to just the subgroup itself, where I'm using the fact here that the identity coset is just equal to the subgroup itself. But then by a big result that we proved a while ago about when cosets are equal, this is equivalent to saying that G is inside of n. Okay, so let's see what we have. We have g is inside of the kernel of n if and only if g is inside of n. But that's exactly the sort of condition that we need to build to show that the kernel of pi is in fact equal to this normal subgroup here. So now I'd like to point out that this whole setup gives rise to a certain isomorphism. And this isomorphism is not very interesting in this case, but it can be generalized to bigger cases. We have g mod the kernel of pi is equal to g mod n, but then equal to is isomorphic with just the identity operation. So we might as well say isomorphic here just to look towards a more general case. But let's notice that g mod n is equal to the image of pi. So we could extend this out to the image of pi. And then we could rewrite this a little bit, maybe killing what's happening in the middle, and we'll see that g mod the kernel of a homomorphism is isomorphic to the image of that homomorphism. And that's actually true for any homomorphism, not just this special homomorphism, and that's the topic of our next result. Now for the first isomorphism theorem of groups. So this is a super important theorem to remember in abstract algebra. So let's suppose we've got a homomorphism phi from G to G2. So I've named the starting group G instead of G1 just for simplicity of notation here. And let's suppose that's a group homomorphism. Then there is a unique isomorphism, which we'll call psi, that goes from the quotient group G mod the kernel of phi into the image of phi. And that unique isomorphism builds the following commutative diagram. So here we've got the projection from G to G mod the kernel of phi. So that simply takes little g to the coset. And then here we've got the map phi across the top. So phi clearly maps into the image of phi. And then this is our isomorphism. So we've got psi, which goes from g to the kernel of phi up to the image of phi. And what does it mean for this diagram to commute? Well, it means that psi of the coset g kernel of phi is equal to phi of g. And the big takeaway here is that g mod the kernel of phi is isomorphic to the image of phi. So this is a super important tool for showing that certain groups are isomorphic. And that's how we'll use it with some applications coming after this. Okay, so now let's go into the proof. Let's notice that psi is defined where its domain is a quotient group, but anytime the domain is a quotient group, a set of equivalence classes, we have to check that psi is well defined. So let's suppose that we have two elements of psi that are equal but perhaps have different names. So we've got x kernel of phi, we've got that coset, and that's equal to y kernel of phi. So that's inside of g mod the kernel of phi, and then, so those are equal. Okay, but what does it mean for those two cosets to be equal? Those two cosets are equal if and only if xy inverse is inside of the kernel of phi. That's from that big theorem that we use over and over again about equality of cosets. Oh, but what does it mean for xy inverse to be in the kernel of phi? Well, that means if we apply phi to xy inverse, we get the identity. And we get the identity up here in the group G2. Oh, but what can we do from there? Well, now we can apply homomorphism rules to split this up into phi of x and then phi of y kind of all inverse equals the identity. Oh, but that means that phi of x must be equal to phi of y just by right multiplying by phi of y. Oh, but by our definition, phi of x is the same thing as psi of x kernel of phi, and phi of y is the same thing as psi of y kernel of phi. But that's exactly what we needed to do to show that this is well defined. We took two elements of the domain that were equal with potentially different names, and we showed that they get mapped to the same place under our function psi. Okay, now let's move on to the other parts of this proof. So next up we'll show that psi is in fact a homomorphism. That's part of it being an isomorphism. Okay, so let's start with psi of the product of two things inside of its domain. But let's recall that the domain is made up of cosets of the subgroup kernel of phi. So there's the product of two elements inside of the domain. But now we'll do the calculation inside of these parentheses to push those two cosets together using the group operation in that normal subgroup or in that quotient group. So that gives us xy kernel phi. But now we can apply our definition of psi, and that'll give us phi of xy. Now phi is a homomorphism, so that gives us phi of x, phi of y. But then we can apply this equality in the reverse direction. And that gives us psi of x kernel phi, and then psi of y kernel phi. And that's exactly where we needed to end up to show that psi is a homomorphism. Now let's show it's injective. Okay, so to show that psi is injective, we'll use that lemma that we just had that said that a homomorphism was injective if and only if its kernel was trivial. So what we'll do is take something inside of its kernel and show that that thing inside of its kernel has to be the identity, but that shows that its kernel is trivial. Okay, so let's do that. So let's suppose G kernel phi is inside of the kernel of psi. Okay, so the word kernel is a lot of places here, but I think that's like kind of okay even though it looks confusing because it gives us the opportunity to practice what context each of these like objects is inside. So this G kernel phi is an element of G mod the kernel of phi, that quotient group. And it being inside of the kernel of psi makes sense because the kernel of psi is a subgroup of this quotient group. Okay, so anyway. Okay, so now since G kernel of the phi is inside the kernel of psi, that means if we apply psi to this element G kernel of phi, then we get the identity inside of G kernel of phi. But that's simply the coset connected to the identity element. We get the identity in the image of psi, but the image of psi is inside of G2, so we get that this is equal to the identity. But now we'll apply our rule for psi. Notice psi takes that coset to the corresponding image of phi. So this tells us that phi of G is equal to the identity. But that's exactly the condition for G to be inside of the kernel of phi. Oh, but if G is inside of the kernel of phi, then that means the coset connected to G is equal to the coset connected to the identity. But that is the identity element inside of this normal subgroup. So we took a seemingly arbitrary element inside of this normal subgroup, which was in the kernel of this map, and we showed that it indeed had to be the identity element inside of this normal subgroup. So that's exactly what we needed to do to show that psi is injective. Now let's show it's surjective. Now we'll finish this off by showing that psi is surjective. So let's take something in the image of phi and then find a pre-image for it. So let's take, we'll call it y inside of the image of phi. Okay, but since it's inside of the image of phi, then that tells us that there exists a little g inside of g such that phi of g is equal to y. But notice that phi of g is equal to psi of g kernel phi. So that actually finishes it off. So we've got psi of g kernel of phi equals phi of g, which is equal to y. So what we did is we found someone in this quotient group that gets mapped by psi up to our arbitrary element here in what is the codomain of our map psi. That's exactly what we needed for psi to be surjective. Now we're going to look at a bunch of application examples for this first isomorphism theorem, starting with a really classic one. Let's take phi going from z to zn, where we take any integer m to the equivalence class associated to that integer inside of zn. So I'd like to point out that most of the time we don't write these equivalence class brackets, but since we're dealing with normal integers over here, I think it's maybe okay to do it, or maybe even a good idea to do it in this case. So now let's first check that it's a homomorphism. So let's look at phi of a plus b. Recall that the operation is addition in both sides. So this is going to be equal to the equivalence class associated to a plus b. But by a pretty classic exercise that I think we did earlier in the course, or if not, is typical in an introductory proofwriting class. This is the same thing as the equivalence class of A plus the equivalence class of B, which is phi of A plus phi of B. So we're good to go there. Everything is in. So we're good to go there. We have a homomorphism. And next, the image is actually everything. And so how could we see that? Well, let's take maybe m to be inside of zn, and note we could really just take any representative from the set 0 to n minus 1. And then what we have is phi of m equals the equivalence class of m, and then we hit everything. So I don't really think there's much to do to show that the image is everything in this case. Okay, so now let's find the kernel. So let's suppose that m is in the kernel of phi, but notice that means that phi of m is equal to the 0 equivalence class. But by the definition of phi of m, that means the equivalence class containing m is equal to the equivalence class containing 0. But then by the definition of these equivalence classes, that implies that m is congruent to 0 mod n. But that means that m is a multiple of n. So that means that the kernel is in fact equal to all multiples of n. So we could write it out like this. We've got 0n, 2n, 3n, dot, dot, dot. But then back in this way, we've got minus n, minus 2n, minus 3n, dot, dot, dot. But in other words, the kernel of phi is the cyclic subgroup generated by n. Or maybe it's this other notation, which is n times z. But again, that's exactly equal to this condition right here. This condition right here says that m is a multiple of n. But being a multiple of n means being inside of there. But now let's see what the first isomorphism theorem says about this. It says that the group over here, mod the kernel, is isomorphic to the image, but the image was everything here. So we have z mod nz is isomorphic to zn. And in fact, if you look at like a graduate textbook in abstract algebra, like for instance Dummett and Foote, they will essentially never use zn. They'll only use this notation z mod nz. And sometimes people use this notation z mod this cyclic group generated by n, but I think maybe this one is more common. So just be on the lookout for that. Now let's go to another example. For our next example, let's take a map phi from dn to z2, and we'll take s to 1, r to 0, and then extend this to a homomorphism. So it may not be extendable to a homomorphism, but you know, we should try to extend it to a homomorphism and make sure everything makes sense. Okay, so let's maybe get going. Let's list all of the elements of Dn. So that'll be E, R, R squared, all the way up to R to the n minus 1. And then all of the reflections will be S, SR, SR squared, all the way up to SR to the n minus 1. Then since R is sent to 0, any combination of R with itself will also be sent to 0. Because, for instance, via a simple calculation here, we should have phi of R squared is equal to phi of R times R, which is the same thing as phi of R plus phi of R, which is equal to 0 plus 0. But that's equal to 0, sort of obviously. Great. So that means that this R will be sent to 0. This R should be sent to 0. Well, the identity is sent to 0 because it has to be sent to the identity in the target group. And down here, this R to the n minus 1 must also be sent to 0. But then we've said that S must be sent to 1. What about SR, SR squared, and so on and so forth? Well, we could likewise do a calculation for that over here. So let's notice that phi of SR to the m, for instance, will be equal to phi of S plus phi of R to the m, because we're extending this to be a homomorphism. And addition is the group operation over here, but that's equal to 1 plus 0, which is equal to 1. So R to the m gets sent to 0 by our previous observation. So all of these get sent to 1. And now under this setup, I think it's a fairly routine calculation to check that this is a homomorphism. You really only have to check maybe the types of elements that you're combining. So if you combine a rotation with a rotation, do you end up with the rule being satisfied for a homomorphism? When you apply a reflection to a reflection and evaluate that at phi, do you see that the rules of a homomorphism are satisfied? And then if you apply a rotation to a reflection, does it also work? And you'll see that it works in all of those cases. Okay, so let's notice that the image is everything just based on this layout of where the elements are sent. So in fact, we have the image of phi is equal to Z2. We hit everything. And then the kernel of phi, well, again, we see where all of the elements go, so we know exactly what the kernel of phi is. It's just all of these rotations. But notice that's exactly the cyclic subgroup generated by the rotation R. It's because we've got R to the 0, R to the 1, R squared, all the way up to R to the n minus 1. R to the n is the identity based on the fact that we're in this dihedral group. So the kernel is simply just that cyclic subgroup generated by the single rotation. Okay, but now applying the first isomorphism, this tells us that Dn mod this cyclic subgroup is in fact simply equal to or simply isomorphic to Z2. Okay, so now I want to explore the possibility of swapping where 1 and 0 goes and see if it still works. Something that seems like would be a nice companion example to our last example would be a homomorphism from Dn to Zn that sends S to 0 and R to 1. That's because R has order n inside of Dn and 1 has order n inside of Zn. But what we'll see here is that this does not extend to a homomorphism, so that means we can't even really get off the ground here. And let's do the calculation right here showing that it does not extend to a homomorphism. So let's look at this. So let's notice that 1 is the same thing as 0 plus 1 plus 0. I think that's pretty clear. But that's the same thing as phi of S plus phi of R plus phi of S. Recall inside of Zn, our operation is addition. But now if we assume that phi is a homomorphism, that means we can put this stuff together to get phi of SRS. But then doing the quick calculation on SRS, you'll see that you get r to the n minus 1 because we're inside of Dn. So this is phi of r to the power n minus 1, but if r is sent to 1, then r to the n minus 1 is sent to n minus 1. So putting this all together, we get n minus 1 is equal to 1, which implies n is equal to 2. Okay, well, what that really tells us is that this is a homomorphism in one case, but the only case that works is where n is equal to 2. And now that we've determined that that's the only place that works, let's maybe look at this a little bit more carefully. Okay, so the way that we'll check that it's a homomorphism is just to see what the image of all of the elements looks like. So in D2 we have 4 elements. We have 2 rotations, E and R, and we have 2 reflections, S and SR. This is actually isomorphic to Z2 cross Z2, the Klein 4 group. So here, E would be sent to 0, R would be sent to 1, S would be sent to 0, whereas SR would be sent to 0 plus 1, which is 1. So that would build our homomorphism. Notice that by this chart right here, this is like pretty clearly surjective. So the image of phi in this case is all of Z2. Furthermore, we can calculate the kernel pretty easily as well. Let's notice that the kernel of phi is equal to the cyclic subgroup generated by S. It's got E and S in there, but look, let's recall that S squared is the identity, so that's the cyclic subgroup generated by S. Now, putting this all together, for this very special case, we see that D2 mod the cyclic subgroup generated by S is in fact isomorphic to Z2. And then I guess furthermore, what we uncovered is that in general, S is not a normal subgroup of Dn if n is not equal to 2. So that means we can't talk about the quotient in any other case except for this case up here. All right, let's look at another example. Now let's look at a nice example that arises from a linear algebra context. Let's take the determinant operation. So that's going to take an input, a 2x2 matrix in our case, and an output, a real number. But since we want everything to be a multiplicative group, that means we need to take GL2R. Recall, that's all 2x2 matrices with non-zero determinant. But then the group that we're mapping to will be the multiplicative group of non-zero real numbers. Okay, so let's check that this is a homomorphism. And I believe we wrote this down a little bit in a previous video, but what I want to do is maybe just use some facts that you know from linear algebra to keep this easy. So let's take the determinant of A times B, and like I said, from linear algebra, we know that this is the determinant of A times the determinant of B. But that's exactly what we need. Okay, so now what about the image? Well, in fact, we can get any real number here. So let's take x to be a non-zero real number. So let's write that with our standard notation. And then we'll also look at 2 cases. So the first case will be x is bigger than 0. Okay, but if x is bigger than 0, then that means the square root of x is also positive. And then we can look at the determinant of the 2x2 matrix, which is the square root of x, 0, 0, square root of x. But just by standard determinant calculations, that'll be the square root of x squared, which is x. So we found a pre-image for this. It is the following like diagonal matrix. So now case number 2 is what happens if x is less than 0. Okay, but if x is less than 0, that means that the square root of negative x is positive. And now we're going to look at the determinant of the following object. So that'll be the determinant of the matrix which has these square root type objects on the off diagonal. So something like that. So notice again, by determinant rules, that will give us exactly what we want it to, x. So either way you get it, if x is positive or negative, we are able to land on the right number. Okay, so now putting these things together, we see that the image of the determinant function is in fact all non-zero real numbers. Of course, when we're coming from GL2R. So now what about the kernel? Well, let's notice that A is inside of the kernel of the determinant if and only if the determinant of A is equal to the identity in this group, which is the number 1. But we've actually got a name for that. What I mean is a name for 2 by 2 matrices whose determinant is 1, and that is SL2. So that means we have A is in the subgroup SL2R. Well, that's actually a very, very quick proof that SL2R is in fact normal in GL2R. Instead of using the definition of normality, we have exhibited it as the kernel of a certain homomorphism. So that's cool. Okay, but what does the first isomorphism say about this setup? It says that if you take GL2R and you mod out by this subgroup SL2R, then you get something that's isomorphic to the multiplicative group of non-zero real numbers. Okay, let's look at maybe 2 more. Okay, so for our next example, let's take our group to be R adjoin X. So that's all polynomials where the coefficients are in the real numbers. And then we'll take our map to be the derivative. So this takes a polynomial and outputs its derivative. And you might say, well, what's the operation here? So the operation will be addition of polynomials. Okay, so let's check that this is a homomorphism. So if we take the derivative with respect to x of p of x plus q of x, by the sum rule for derivatives, we get p prime plus q prime, which is equal to the derivative of p of x plus the derivative of q of x. So we're good to go there. This is a homomorphism. Now, what's the image? Well, I would say that the image of this is, in fact, all polynomials. So this is onto. And you can maybe see that with the following example. Let's take the derivative with respect to x of a0 times x plus a1 over 2 times x squared plus a2 over 3 times x cubed plus all the way up to a n over n plus 1 times x to the n plus 1. But notice by applying the power rule a bunch of times, that's going to give us a0 plus a1x all the way up to an times x to the n, which is an arbitrary polynomial inside of R adjoin x. So we can achieve an arbitrary polynomial. Now let's find the kernel. So I think it's pretty clear that the kernel of this derivative operator is simply equal to the constants. So this is going to be equal to r inside of rx. That's because the derivative of a constant is 0. I don't think there's anything else that needs to be said here. So let's notice that in this case we get something pretty interesting, that when we take r adjoin x and mod out by r, we just get something which is essentially a different copy of r adjoin x. So the isomorphism theorem is not super interesting in this case, but I think the example itself is interesting. Okay, let's look at one more. So for our last example, let's take the map phi, which goes from z6 to z15, and it takes n to 5n. Where on each side, we're assuming that that is the equivalence class. So technically here you need to check that this is well defined, but we've done that a couple of times in this video already, so maybe I'll leave that as a bit of an exercise to you to check that this is indeed a well-defined map. Now let's check that it's a homomorphism, but I think that's pretty clear as well. Notice that phi of m plus n is 5 times m plus n, which is 5m plus 5n, which is phi of m plus phi of n. Just recall that these things are happening in different places. This m plus n is happening inside of z6, whereas all of these additions over here are occurring inside of z15, but the addition works out. Okay, now let's calculate the image, but here we're going to use the fact that z6 is equal to the cyclic subgroup generated by the number 1, or the cyclic group generated by 1. So that tells us the image of phi, well, that's just the image of the whole group z6, but that'll be the cyclic subgroup of z15 generated by 1. But then we can calculate that. So phi of 0 times 1 is 0. Phi of 1 is 5 because we multiply by 5. Phi of 1 plus phi of 1 is 10. And then phi of 1 plus phi of 1 plus phi of 1 is 15, but that's back to 0. So that closes this thing up. Let's also notice that this is isomorphic to Z3. So it's a 3-element group, so it's got to be isomorphic to Z3. And now let's calculate the kernel. So let's maybe notice that if n is inside the kernel of phi, that's equivalent to saying that phi of n equals 0 in Z15. But that's equivalent to saying that 5n is equal to 0 inside of Z15, just by the definition of our phi. But notice that's the same thing as saying that 5n is congruent to 0 modulo 15. But notice 5n is congruent to 0 mod 15 if and only if n is congruent to 0 modulo 3. But remember that we're inside of Z6. So the only things that are congruent to 0 mod 3 inside of Z6 are 0 and 3. That's because Z6 only contains 0, 1, 2, 3, 4, 5. The only things that are multiples of 3 are 0 and 3. But notice 0, 3 is the subgroup generated by 3 inside of Z6. Okay, so now the first isomorphism theorem in this case says that Z6 mod, the subgroup generated by 3, is in fact isomorphic to the image, but we just showed that the image was isomorphic to Z3, so this is isomorphic to Z3. And there's actually a more general way of talking about this, which we will do, in an upcoming video. Okay, now I'll leave you with some warm-ups. The first is to completely describe the homomorphism phi from U36 to Z6 that takes 5 to 1. Be careful here because U36 is a multiplicative group, whereas Z6 is an additive group. Next, let's define phi from multiplicative group of complex numbers, so that's everything except for 0, to the same multiplicative group of non-zero complex numbers. That takes z to the 4th power of z. Let's show that's a homomorphism and find its kernel. Then finally, let's define phi from R to the non-zero group of complex numbers by x going to e to the ix. Then next, let's show this as a homomorphism and use the first isomorphism theorem to make a nice isomorphism. And that's a good place to stop.